Thank you for joining. Welcome, everybody. We're going to be spending this hour talking a little bit about artificial intelligence, some of its applications, a little bit of the computer science and mathematics behind it, pretty briefly, and then talking a little bit about some interesting applications, some stuff that you can do with it, its potential impact on society over the next couple decades potentially, and kind of where we're at in the market right now. A little bit about myself before we get started. If you have questions, feel free to put them in the chat box over on the side. And then I think we may address them as we go, or spend a little bit of time at the end, depending on whether Beth wants to chime in here. So a little bit about myself. I don't know whether you can see this box or not, but I'm an emerging technologies consultant with Ernst & Young. My background is in physics. Prior to working as a consultant, I worked on a couple of startups and actually founded one myself. Worked on that project for about a year. And now I work with a variety of clients within the Fortune 500 to help them understand emerging technologies, graph databases, artificial intelligence, et cetera, and the potential applications and impacts on their business right now and moving into the future. So the agenda for today is to spend a little bit of time talking about artificial intelligence, what it is, going through a couple applications, and hopefully being entertained along the way. So I guess we'll just jump right into it. Wanted to start with a motivating example. This is something that was in the news probably around 5 years or so ago. There was a company called DeepMind that was acquired by Google. And they worked on teaching an artificial intelligence to play the game of Go, which is an ancient Chinese board game. And the interesting thing about Go is that it's many, many more times complicated than chess. So way back in the 80s and 90s, there were continuing competitions between IBM's Deep Blue and the best chess masters in the world. And Deep Blue eventually got to the point where it was able to defeat many of those chess masters. So then the next step was to move on to playing Go, which by some measures is about 6 to 7 times more complicated than chess. And there's actually more board configurations in Go than there are atoms in the universe. So it's an extremely difficult problem. And they trained the artificial intelligence from scratch by allowing it to see games that actual humans had played against one another and learn over time. And eventually the artificial intelligence was able to, just like previously with the chess example, was able to beat some of the top players in the world, and even invented some new strategies that humans over the long history of Go had never come up with. So it's just kind of an interesting example of some of the early applications, maybe not applications in work or the market, but an interesting example of something that you can do with an artificial intelligence that got a lot of publicity and was purchased by Google for quite a large amount of money so that they could roll that technology into some of their other projects. So what is artificial intelligence? We'll start with a couple other examples that you might see day to day. Many of your Google search results are driven by an artificial intelligence algorithm that's running, that's selecting based on the keywords, et cetera, that you put into your search bar to give you the results that are most relevant to you. Self-driving cars, still very much an active area of development, and it'll be interesting to see how those develop over the next couple years here. Face recognition with Apple Pay. If anyone has ever used the face recognition on their iPhone to purchase things or to open it up. Shazam, I don't know if anyone remembers, but is an app that you can use to have it listen to the audio around you. If you come across a song that's playing in a public place and you want to know its name, it'll go and listen to the music, and based on that small snippet, use an algorithm to figure out what the song is. Alexa, along the same lines, rather than applying the algorithm to a song, it transcribes voice commands and executes them to, against a predefined set of actions to allow you to do anything from search the web, turn on music, turn on the lights in your house. Your Facebook feed, similar to the Google search results. MRI analysis. We're gradually getting to the point now where using algorithms, the image recognition is actually able to outcompete many individual doctors in identifying cancers or other issues within MRI images. So within a relatively short period of time, the majority of MRI analysis may be done by machine learning algorithms. Finally, another interesting example was a company called Blue River, which was purchased by John Deere a number of years ago. And essentially, it was just a bunch of grad students from Stanford that went out and took a bunch of pictures of corn and other vegetables and learned to classify and predict basically the health of crops based on photographs that they had taken, and then was eventually acquired by John Deere. So some interesting examples. There's a lot of hype around AI and machine learning right now. I would say we're probably somewhere around here in the middle of the typical hype cycle. Usually what happens with new technologies is everybody gets, there's an advancement, everybody gets really excited, and then people realize how difficult it is to really put many of these things into practice, and you learn the boundaries, and there's a period of disillusionment. I think we're probably close to that point now. And then gradually, as people learn to get better at learning how to use these things in practice, we move on to the plateau of productivity, where things really actually have an impact in a lot of areas in the market. Couple notes on machine learning and artificial intelligence. They're not exactly the same. Machine learning is considered a subset of artificial intelligence, but generally speaking, when you hear machine learning, just think AI. It can be more or less used interchangeably. Additionally, people often have questions about the difference between statistics and machine learning. The distinction is generally that machine learning is a similar discipline, uses similar techniques, but the key difference is that the algorithms that you're using within the machine learning space generally get better as you feed larger scale data to them. And they improve over time as they learn from new insights that you're feeding to the algorithm. A little bit more background on some of the things that you can do or the problems that you might want to solve with a machine learning algorithm. Sort of the prototypical examples are classification and regression. We'll get into some more exotic examples of what you can do with these algorithms briefly, but a lot of the early applications you can think of, for example, within image classification. Is there a cat in this photo or not? And there are many competitions that they run either annually or once every 2 years, based on a large set of photographs, where machine learning teams compete to identify what's in the photograph, to localize and put a box around, say, a cat if it's in there, or a car, or a person. to gradually figure out what algorithms are best for executing these types of tasks, so that we can take that research and turn it into applications in the market. Regression problems would be, if you're thinking about something within a business context, would be learning the relationships between things. So as we scale our customer base, what happens to our revenue, right? Very simple example, but most problems that you're trying to solve outside of sort of the like I said, the exotic examples that we're going to talk about fit mostly into these two categories. So it's a good starting place when you're thinking about how to classify a problem that you're trying to solve with an algorithm. A little bit about the history of why machine learning and artificial intelligence has become a discipline over the last couple decades, or really caught on within the last couple decades. The sort of founding of the field happened when Frank Rosenblatt invented the perceptron in 1958. The perceptron is basically just a mathematical representation that was invented to kind of sort of mimic the operation of neurons within the brain. So if you kind of squint, they sort of look similar to one another. And essentially, you just take a bunch of these perceptrons and you link them together into a network, and that's all a neural network is. So you feed information in one end, and some kind of a prediction comes out the other. And as you train them, the perceptrons that form the layers in the middle change and evolve and get better at making predictions, so that they can evolve over time, similar to that example that I gave about the difference between a statistical algorithm and a machine learning algorithm. So that's a little bit about neural networks and the way they've developed. Training them has developed as a discipline. Part of the reason why it's happened now, even though the perceptron was invented way back in 1958, really has to do with how much cheaper computing power has gotten. So your phone is significantly more powerful than the computers that we use to send people to the moon. And so as compute continues to get cheaper, the huge amount of data processing that's required to make artificial intelligence work has really allowed us to get to the point where we can train these algorithms and allow them to work more effectively. One way to kind of think about some of the algorithms that are out there is to kind of bucket them based on sort of the senses that we use to navigate the world. For example, vision would be facial recognition, or the MRI analysis that we talked about. That's achieved with something called a convolutional neural network. So potentially a good thing to go and research on your own. Hearing would be audio transcription or Alexa. That's achieved with something called a recurrent neural network that allows it to keep track of data that changes over time rather than an image, which would be static. Thinking about taste and smell, you can model taste and smell are achieved by the interaction between chemicals, and this can be modeled using artificial intelligence algorithms. For example, many of the pharmaceutical companies use machine learning and AI in order to better understand the interactions between drugs and aid in drug discovery. Really reduces the cost in drug discovery because it allows them to get a good sense of what pharmaceutical compounds, what molecules are going to potentially look similar to maybe other drugs that have a similar effect, and really allows them to hone in on a couple of molecules that they want to run clinical trials on, as opposed to running a clinical trial on, all kinds of things that may turn out to not be very interesting that they could have ruled out using an algorithm ahead of time. So a couple other interesting applications that are really coming to the fore over the last couple of years. One of them is something called a generative adversarial network. And I won't get into details too much, but essentially what this is it's two networks that compete with one another. One of them is called a generator and the other is called the discriminator. And essentially all it does is the generator creates something and the discriminator decides how good it is, essentially. And they compete with one another over time and get better as they compete with one another in order to more effectively achieve a task. So one example, and you can kind of use your imagination about what some of the implications of this might be. But in this case, it's the generator has been asked based on being given a string of text to generate an image of a bird. And based on the description of the bird within the text, it will generate a different set of characteristics for that bird. And then the discriminator's job is to go and compare the images that have been generated by the generator and compare them to real images of birds. And so in that way it says, hey, I think this one is artificial and this one is a real image. And by competing with one another, they continue to get better and are able to produce some of these images that you can see here. We'll zoom in a little bit on these so you can have a look. And some of them are really pretty convincing. For example, this one over here, at a glance, it really does look like a photograph that you might see. This one here looks pretty good. There's, some of them are a little bit blurry or grainy, or are maybe missing some things that that we as humans know that a bird is supposed to have. Like this one doesn't appear to have an eye, because the algorithm itself doesn't actually have a concept of what a bird is. So it's just learning from the data, and it makes mistakes like that we know because we have a representation of what a bird needs in our heads. So it's learning over time and getting better at that. And that's one of the difficult things about training an artificial intelligence to do things, is that it doesn't have these prior representations of things that that we know to be a bird ahead of time. So it just has to learn from the data that it's given. So one of the big challenges within the space. Additionally, you can use the same technique in order to generate sound. So the same technique has been used to train a network on a bunch of classical music in order to create a classical music piece that sounds like a given composer, like Chopin or Mozart. And it's an interesting thing that maybe you can look up after the talk is over. So if you look up generative adversarial networks and then put in Chopin, you can actually listen to the music that it's generated yourself, and they're pretty good. There's moments in there where you could maybe be convinced. So it's really come a long way over the last couple of years. And there's actually some interesting applications here as well. There have been a number of composers, as well as companies that are in the music production space that are looking into the same technology in order to generate either ideas for songs or parts of songs to create interesting melodies that maybe they can pass on to their artists to expand into sort of full-fledged stuff that they hope will catch on and produce a hit within the market. The same technology can be used to generate realistic video and audio. So we'll pull up quickly a video of this deepfake technology. So one of the things that you can do with it is you can generate video of a person speaking. and that's called, or doing whatever, playing baseball. So you feed the algorithm a bunch of video of people doing things, and then you can train it to transfer the style or the look of a specific video that you want onto another image. So you might take a video of yourself talking, and you might train an algorithm on thousands and thousands of hours of Obama giving speeches, and you would be able to use an algorithm to make it look like Obama was saying the things that you were saying in the video. So this has pretty serious political implications that it's getting harder and harder for the general population to spot these videos. So it's important to for lawmakers to keep track of this technology and to understand the ways that it might be used by foreign powers or individual actors to create propaganda or disseminate misinformation. I can switch here and show a quick video of what this looks like. So we left the sound off, but so for example, it's been used to by a number of people to take Nicolas Cage's face and put it on a variety of other actors or actresses within movies, and similarly with Steve Buscemi. So kind of an interesting thing, and pretty entertaining in my opinion. So you can spot the difference there pretty easily, partially because it's mostly those actors being put on women, so they still have their hair and everything else, so they're easy to spot, but much more difficult when you're maybe replacing the video with the entire thing rather than just swapping out the faces. Okay, back to the slides. And another thing to keep in mind as well is that these things may be, for example, if the style transfer using the generated video is being used to create video that's being pushed out to the population of that are native speakers of maybe the politician that you're applying the style transfer to, it's a little bit easier to spot the difference. But for other people in other countries that may have English is not their first language, or vice versa, it can be even more difficult to tell based on the tone or the sound of the voice whether it's a real or fake video. So a couple things to keep in mind there. Another interesting application that we won't get too deep into this, or actually read it in detail, but a group called OpenAI, that's actually funded by Elon Musk, created a network that was trained on all of the articles that have ever been linked to Reddit, and trained an algorithm based on an initial prompt to generate an article that was consistent with the couple sentence prompt that they gave it. And the amazing thing about what they were able to achieve with this algorithm was that it was able to produce an article that picked up on the key themes within the prompt that it was given, and was even able to understand the relationships within the text that it was given between maybe individuals, or even get a sense of geography. So for example, within this prompt that's about a group of scientists discovering unicorns in South America, and those unicorns being able to speak English, there's a couple excerpts from the article that it produced where the algorithm was able to identify that the prompt was about South America. So we should use a research scientist that has a Latin last name, and select a university that was within South America, and talk about a mountain range that was within South America as well. And further down in the article was able to keep track of the fact that the unicorns that were discovered were able to speak English. And then amusingly, because if anyone has ever been on the Reddit community, there's definitely some interesting articles that get linked. So the article that was generated sort of devolved into sort of a conspiracy theory about whether the unicorns had evolved from a race of humans. So pretty interesting in terms of what they were able to achieve. Definitely a big step forward in creating artificial intelligences that are able to understand and generate language. We could see in the future maybe having algorithms that generate reports based on things that happen in the market or in the news without having to necessarily have a human reporter that's actually sitting down and writing articles. Probably sooner rather than later, we'll see those things happening with articles that maybe don't require a huge nuanced amount of analysis, but are more reporting on what happened, sort of verbatim, and leaving the very skilled reporting to reporters that have views on the ground. So something interesting that may be happening over the next couple of years. Another thing that you can do with an artificial intelligence is generating an artificial intelligence that actually takes action within an environment. At their core, creating an artificial intelligence that takes action is similar to the classification problem that we talked about before, where you're identifying whether there is or is not a cat in this photo. The reason why is because the artificial intelligence that's taking an action at each given moment is actually generally making a decision about what to do next from a predefined set of actions that it can take, right? So for this reason, some of the first applications that this type of artificial intelligence has been used for was to play Atari games, and a variety of groups, including a couple of groups at Google, were able to produce artificial intelligence called agents that act in an environment to outperform humans at playing Atari games like Pong. The key difference between a simple classification algorithm and one that acts in an environment and chooses to, to take an action at each moment in time is that every time the computer takes an action, it's then reassessing the environment that it's acting in and deciding whether the action that it took brought it closer to its goal or farther away. So it's a little bit more of a dynamic system that is able to evaluate the actions that it's taking in real time and change its behavior as it takes actions in those environments. So there's a couple videos of this in action that I wanted to share. So for example, the same OpenAI group that I mentioned previously trained an algorithm that was connected to a sort of a robotic human hand to manipulate a block. So essentially what it's learning to do entirely with no pre-training, it's just a neural network that's able to learn how to take feedback from its hand sensors to turn this block around and face it towards a predefined goal that the researchers were feeding to it. And then you can also see the camera up here that's allowing it to keep track of what the orientation of the block is and whether each of the movements of the fingers is bringing it closer to the goal that it's trying to achieve. So kind of interesting. This is an example of something that's, over the first couple of years of life, we learn to do, and then after a relatively early age, we're able to do more or less flawlessly. But it's an example of how difficult and how complicated the processes that are going on in our brains actually are, as we're taking into account feedback from our environment and learning how to do things, and why it takes so long for us as biological organisms to develop and learn to effectively navigate our surroundings, and why it's something that's difficult to replicate using a machine, because there's more to it than we often give credit for. Additionally, within sort of a simulated environment, Google's DeepMind group, that was an offshoot of the same one that played Go that I mentioned at the beginning of the talk, taught a small figure like this to learn to walk and to navigate obstacles within a simulated environment without any understanding of how to walk prior. So it took thousands of training hours and many iterations of training in order to allow the artificial intelligence to learn to walk and navigate. And essentially, it's giving the AI the goal of getting to the end of the stage here, where it gets rewarded by moving closer and closer to the end of the terrain that it's navigating, and then gradually learning to balance and jump and run, etc. So, kind of interesting. As mentioned, there's the algorithm is gradually, it has something called a cost function. And the cost function is the mathematical representation of what the algorithm is trying to do. So in that case, with DeepMind, the goal, the cost function was improved by getting closer and closer to the end of the stage that it was navigating. But these things are difficult to design because the world that we exist in is really complicated, and so it's hard to know exactly, as a computer, how to represent mathematically exactly what's going to allow it to achieve its goals, more or less. In this example, this is the same OpenAI group that was doing the dexterity challenge, that was teaching an artificial intelligence to play this boat racing game. And the goal of the game was to go around this track. But after thousands of training hours, the boat was just trying to maximize its score. And it learned that rather than going around the track, if it just stopped in this little area and just went in circles, picking up these power-ups, it was actually able to get a higher score than going around the track and following the object of the game. So because the AI doesn't have any inherent notion of what boat racing is, or that it should really be going around the track, it got stuck in sort of this local area where it was like, okay, well, I get a better score by just going in circles here, so I'm just going to do that. So a good example of sort of pitfalls and why it's difficult to train these algorithms to do things that you may not expect to run into from the outset. Okay. So I think we've more or less covered this. If you're interested in the algorithms that are taking action with an environment, that's called reinforcement learning. So it's how they trained AlphaGo, and the agent is the artificial intelligence that's
For those of you watching the program, just hang on. Obviously, we lost Ian. Hang on, and hopefully we'll get him back in another minute or two. Yep, so he put himself out and he'll bring himself back in again. So just hold on and he'll be back in just a second. All right, you're back, but you're still muted, Ian. There we go.
Can you hear me? Oh, can you hear me?
Yes, we can hear you. You're back. We're all good.
Great. I'll reshare my screen here as we kind of move on to the last section of the talk. Sorry about the screen share crashing there. I don't know, Beth, if we want to bring up any questions. The last section of the talk is a little bit about sort of the impact of artificial intelligence on the market and how it's likely to impact certain job roles over time. So maybe if there's any questions that we want to cover before we move on to the last section about what we've covered so far, we could do that.
Excellent. I don't see anything in the chat box right now, but let's give people 15 to 20 seconds. If they want to start typing in a question in the chat box, now's a good time to do it on anything Ian's already said, and then he'll continue on. And you're always welcome to type in a chat or a question at any time, and then we'll either get to those at the very end or I'll interrupt Ian with them if they seem pertinent. So I'll just give it another 10, 15 seconds. I'm not seeing any questions come up, so why don't you, Ian, go ahead and continue. And
No
then
worries.
if there are any other questions, again, please just type them in the chat box and we'll get to those.
Sounds good. Okay. So a little note on artificial intelligence and its applications to various job roles and what it's currently able to do, what it's not able to do, and what might be around the corner. Excuse me. So as an example of, we talked about AlphaGo being able to play Go, right? But that's an example of a very deep AI that's able to perform one task very well. And this is one of the main sort of unsolved problems within the space of artificial intelligence is we really don't know how to create what would be called a general artificial intelligence that's able to perform lots of tasks well, as opposed to creating an AI that can just do one thing excellently. And in order to have a big impact on the market, we may not need to do that, but general artificial intelligence is kind of what people are worried about when they think about, whether there's any danger to humanity from creating an artificial intelligence that's, say, smarter than us. And we'll talk a little bit about, briefly after this, about those issues. But because so we'll move on. We'll talk about that in a moment. So far we don't know how to create algorithms that can perform lots of different tasks well. It's important to keep in mind sort of the difference between automation. When you're thinking about your job role or some other job role within an organization or some tasks that people are achieving, it's important to keep in mind the differences between automation and artificial intelligence. So there's lots of sort of repetitive tasks that can be pretty easily be set into a predefined set of rules that you can do with just a basic computer program without needing anything like machine learning. And you'll run into a lot of scenarios where there's a lot of companies that are offering services where they say that it's machine learning, but it's really not under the hood. It's mostly just a type of automation or some sophisticated program that they put together that's not actually true machine learning or AI. So it's important to be able to spot the differences between those different applications. So things that are good use cases for machine learning is when sort of you may have lots of edge cases where the boundaries between what to do with a piece of data are very fuzzy. And you can't just, or you have a task that maybe changes over time depending on the inputs rather than, having something that's very, very repetitive and predictable. So because most of these machine learning algorithms are good at doing are very deep but not very broad, there's often applications, you can think of a job as sort of a bundle of tasks that an individual manages rather than often a single task that you're executing. So for this reason, people talk a lot about artificial intelligence taking jobs, but mostly what it's doing is shifting job roles as people work closer with algorithms to achieve certain things, where you may have an algorithm that's really good at doing one role.
Ian, we can't hear you anymore. Ian, can you hear me? Uh-oh. Hold on a minute. Let's see how long it takes them to find out that we can't hear him. Ian, can you hear me? We can't hear you. We haven't been able to hear you for about 45 seconds. I can see your mouth moving, but I still can't hear you.
Can you hear me?
Okay, now we can hear you. We lost you about a minute ago. So you were just, can you hear me? Ian?
Beth, can you hear me?
Yes, I can hear you, but can you hear me?
Okay, not sure why I got muted, but I'm going to keep going here. So people's roles are shifting. You can, since the Industrial Revolution, over the last 50 years or so, 50 to 70 years, we've more or less transitioned from a manufacturing-based economy within, say, the United States to more of a service and information-based economy. And so although artificial intelligence has a big impact within this space, or may have a large impact within this space over the coming years, it hasn't proliferated to the extent where we would necessarily think about, totally being, replaced by algorithms, right? Part of the reason why is because we have a lot of automation and algorithms that go into manufacturing, but if you have an economy that's maybe 20% manufacturing versus 80%, the inclusion of an algorithm and automation within that portion of the economy is going to have a much smaller impact on most people's roles. So you can think of a lot of jobs that people do that are, very, very difficult to automate within, broadly speaking, the service sector, like a lot of service jobs within restaurants, teachers, et cetera, consultants like myself, doing lots of different things, or very complicated tasks that require a bunch of different bundles of things that you're doing that change day to day that that aren't likely to be replaced by an algorithm anytime soon. And so you would expect, if we were in a position where everyone's jobs were being eliminated left and right by algorithms, then our per capita productivity. There's some argument within economists about how these numbers are measured, but over the last decade or so, our per capita, so per individual productivity, has actually been slowing down since around 2007. So if we were in a position where everyone was getting automated out of a job, you would think that we would be really efficient in terms of the amount of productivity that we're getting per individual, but that doesn't seem to be the case yet. But it's hard to know what might be just around the corner. So we mentioned a little bit about needing some kind of a more general artificial intelligence that can do lots of different things. That would, like I said, that would be sort of general AI, because the world is very, very high dimensional, aka very complicated. Lots of different things that you might want to do, or approaches that you might want to take in order to achieve a goal. And we really have no idea how to teach an artificial intelligence to do that. Additionally, we really don't know. There's a little bit of a shift within the AI community where the approach for many years was to never provide any type of sort of representation of things other than simply the data that we're feeding to the AI program, and to just have it learn based on the data that's related to the task that it's trying to achieve. But because we don't understand cognition very well, we don't understand why we are conscious or why we're able to do the things that we're able to do, we really don't know much about what types of things might be inherent in our brains from the time that we're born, that would be sort of the nature versus nurture argument. So we don't know what sort of predefined concepts of, say, up and down and left and right that we might need to bake into an algorithm to help it kind of understand the world a little bit better in order to achieve more of a general artificial intelligence. So that our misunderstanding of sort of how to achieve general artificial intelligence is rooted in the fact that we really don't understand cognition very well. So because we don't understand that problem very well, it could be just around the corner. But to a certain extent, it's been just around the corner for the last 30 years. So nobody really knows when there might be a radical shift. So it's a difficult thing to predict. Interestingly, though, the networks within your brain that allow you to do things actually aren't very deep. So it's actually something of a mystery within sort of the artificial intelligence field, why we haven't been able to effectively model the brain. And it's an active area of research. We know based on how quickly the neurons in your brain interact with one another, roughly how complicated each action that you're taking is, because the time it takes for one neuron to send a signal to another, it takes a long time relative to the amount of time that it takes for one part of a computer to interact with another. So we know that, for example, when you see a loved one and you recognize that that's them, it takes only a couple milliseconds. And so there actually can't be that many layers deep of neurons that are involved in that process. So if we understood those representations within the brain, you would think that we would maybe have the computational power to create a representation of those within a computer, but it's really that mystery of exactly what that quote unquote encoding or representation of the world within our brains is that makes it very difficult to recreate within an artificial intelligence. So a lot of people wonder about, once we have a general AI, whether the robots are going to kill us. Part of the reason why is because you can think, if you think back to the example of the boat within the video game that was sort of just doing circles, and rather than doing what you would sort of expect a human to do because they understand what a racetrack is. There's this idea that we may create maybe a general artificial intelligence that can do lots of different things if we're able to figure that out, but doesn't have the same value structure that human beings do, for example. Say we have sort of an inherent understanding of the value of human life, and a variety of other moral constructs that there's a big discussion within philosophy as to whether those come from society or whether they're built into us from birth. So that's a big philosophical discussion that's a little bit outside the purview of this talk, but because we don't understand those things very well, we don't know whether if we created a general artificial intelligence, whether it would think like us or not. So just like the boat going around the track endlessly rather than following the racetrack, you could imagine maybe creating a general artificial intelligence that's goal was to make paper clips. And you might give it the task to make paper clips, and the artificial intelligence is happier when it makes more and more paper clips. But because it doesn't understand, what human beings are or what to value based on any human systems or society, it might just decide that that every atom in the world would be better if it was a paperclip. And if it was truly able to continue to learn and improve on itself very, very quickly, and was connected to the internet and was able to learn more or less the extent of human knowledge, and turned out to be smarter than any human being that's ever lived, it might be able to achieve that. So these are the types of sort of thought experiments. It sounds a little bit wonky, but it is an area that's being actively sort of discussed among artificial intelligence researchers, and people are really focused on AI safety and what might happen if we do make a big breakthrough within general artificial intelligence and create an AI that's able to do something that's able to turn out to be much smarter than any human. And at the end of the day, it may turn out to be a fantasy, but it may also be something that could happen if we have a big breakthrough in terms of understanding what cognition is and learn to recreate it within a computer. So I'll end a little bit with a couple resources that would be interesting to look into. If you're interested in the sort of the philosophical side of things, it's a little bit dense, but there's a book called Superintelligence from an author named Nick Bostrom, who's a philosopher and computer scientist that thinks a lot about AI safety. Like I said, it's a little bit dense, but it's an interesting read. Many of you may have heard of the author Yuval Noah Harari, and he's written a couple of books that involve the potential future of artificial intelligence, as well as sort of reviews of technology in the past. One of the good ones, he's written another book in the meantime called, I think it's 10 Questions for Modern Life or something like that. I don't remember exactly, but if you look up the author, Yuval Noah Harari, it'll come up. And it's pretty good. He also wrote this book called Homo Deus, which is similarly a discussion of where we may be going next, sort of as broadly as a species, and it talks a lot about artificial intelligence in there, and what might happen in the future. If you're interested in actually getting into the field yourself, or just digging a little bit more into the technical details, there's a guy called Andrew Ng. If you Google him, he's got a number of courses that are really excellent introductions to the space that go into the mathematics behind neural networks, but are really focused on sort of a broader understanding of sort of applications, and if allow you to go in, and if you have a basic understanding of how to code in Python, can pretty quickly pick up a couple skills and to build your first neural network to apply to a task. So it's a good place to start. So thanks for joining. It's been fun to talk to you. Maybe we have a couple of questions now.